Welcome to this lecture. If you remember, in the previous lectures we had looked at some basic aspects of real time operating systems, and then we looked at some simple schedulers, the clock driven schedulers, and then we looked at the event driven schedulers, and we found that the rate monotonic scheduler is the one which is simple, and it can meet the demands of the practical applications, and that is the one which is actually used widely. Even all commercial real time operating systems do support rate monotonic scheduling. But in our discussion on the rate monotonic schedulers, we had assumed the tasks are independent, in the sense that they process on their own local data and there is no communication whatever required among these tasks. But then in almost every real application, the tasks need to share resources, and today in this lecture we will see that resource sharing introduces complexity. We need to change our analysis, the task scheduling analysis, and we need to have new algorithms to be able to share resources. Let us get started with that. We were worried which tasks should run at what time, and that was our simple scheduling problem. If we consider CPU as a resource, we can say that CPU is a serially reusable resource. What we mean by a serially reusable resource is that at any time one task can run on the CPU, but at the same time we must remember that the simplifying thing that is there is that a task which is running on the CPU can be preempted at any time without affecting the correctness of the result of the task. Or in other words, even though CPU can be used by only one task at a time, but then when we have a higher priority task, we can always preempt a lower priority task and later run the task from that point where it was preempted, and still our results will be correct. But then now we are going to look at resources which are not serially reusable. These are the non-preemptable resources, and also we will look at the critical sections. A non-preemptable resource is one where once a task is using the resource, we cannot preempt it any time that we need to another task to run, need to wait until the task completes use of the resource. Now, let me ask you this question, that can you give some examples of non-preemptable resources normally discussed in a first level course. So, many of you would be possibly be able to answer this question, that the examples of non-preemptable resource are many. For example, a file, a data structure that is shared among the tasks, devices, and so on, which once a task starts using, it must use until a point where the results are consistent, and then only it can be preempted. So, files, data structures, devices, etc., are examples of non-preemptable resources, where one task once it starts using these resources, it must complete or come to a logical end of use of these resources before it can be preempted, otherwise the results will be inconsistent. Just look at the example of a array of data, and then one task has changed only some part, or maybe it has just read some part, and then before it could write we preempted it. Then another task which started using the resource overwrote the data, and then the task that had read it has got the old data. So, it becomes inconsistent. It should have read the data and then written back the result, then it would have left it in a consistent state. Now, the next question that we would like to ask is that what are critical sections? We know what is a non-preemptable resource and what are some examples of non-preemptable resource, but then what is a critical section? Again, it is based on what is discussed in a first level operating system. If you look back to your books, the first level operating system course, you will find a critical section is a piece of code. It is a part of the program in which some shared non-preemptable resource is accessed. So, a critical section is a section of the code in which some non-preemptable resource is accessed, that is read and written, and this section of code is called as a critical section in almost every operating system book and literature. But then we know that when a task is executing its critical section, it should not be preempted, because if it is inside its critical section, it is executing its critical section and it gets preempted, then the result will become inconsistent, wrong results. So, what are the traditional operating system solution to execute critical section? Again, if you remember, it is semaphores. If you do not remember, you might have to look back at your operating system book. But in a real time application, when the task share resources, we can't really use a semaphore. The semaphore causes severe problems in a real time application. It causes priority inversion and unbounded priority inversion, two very bad problems, and unbounded priority inversion can cause a task to miss its deadline and cause the failure of the application. So, these are two important problems that arise if we use a traditional operating system solution for tasks executing their critical section. Let us look at these two problems, priority inversion and unbounded priority inversion. First, let us look at priority inversion. To understand what is priority inversion, let us assume that a task instance, that is a job, is executing its critical section. And we know that when it is executing its critical section, then it cannot be preempted, and for this purpose, let us say we use a solution like a semaphore. So, the task invokes the semaphore and then starts using the critical section. But then, since the task cannot be preempted when it is executing its critical section, a higher priority task that has become ready in the meanwhile would have to keep on waiting, because the task executing its critical section cannot be preempted, and it may so happen that the task which is executing a critical section is a very low priority task, maybe a logging, result logging or something, and now we have a very high priority task, critical task which has become ready, but then it waits before the task that is executing releases the semaphore. So, this situation is called as priority inversion, and let me just summarize it again, because it is an important concept. The term priority inversion implies that when a low priority task is executing its critical section and a high priority task that is ready keeps on waiting until the low priority task can be preempted. So, the high priority task is ready and needs the resource actually. If it is just ready, okay, if it does not need resource, it can be executed, but then the high priority task needs the resource, and the low priority task cannot be preempted from using its resource, and therefore, the high priority task keeps on waiting for the low priority task to release its resource. We just give an example of a priority inversion. Let us assume that a low priority task T L shown here is holding a resource R and doing some computation on R, and this R is actually a shared non-preemptable resource. Now, a high priority task needs that resource, but until the low priority task actually completes using the resource and releases the semaphore, the high priority task cannot access the resource. So, the high priority task keeps on waiting, and if the low priority task holds the resource for a long time, the high priority task is of course going to miss its deadline. But as we will see now that priority inversion by itself is not too bad. We can solve the priority inversion problem with careful design, but what really is a problem which is hard to solve is unbounded priority inversion. Let us try to first understand unbounded priority inversion, and then we will see why it is difficult to solve and how can the simple priority inversion problem be solved. To understand unbounded priority inversion, let us consider the following situation. We have a low priority task that is holding a resource. So, it is executing its critical section. Now, in the meanwhile, a high priority task is waiting for that resource, and because the low priority task holding the resource cannot be preempted before it completes its uses of the resource, the high priority task is waiting. So, this is a simple priority inversion, but then the unbounded priority inversion arises when there are many intermediate priority tasks which are not needing the resource, and therefore, they can execute and use the CPU. The low priority task which was holding the resource cannot make progress with its computation, because the intermediate priority task are not needing that same resource, they therefore do not block, they just keep on executing on the CPU. The low priority task cannot complete its execution, just keeps on holding the resource and waits for the CPU, but in the meanwhile the high priority task is waiting. So, this is really a bad situation. The low priority task is holding a resource, okay, fine, and the high priority task is waiting, that is a simple priority inversion. But an unbounded priority inversion situation occurs where the low priority task has been preempted from using the CPU, and therefore, the low priority task is not able to make progress with its resource uses, and the intermediate priority tasks keep on executing on the CPU. Just to explain the unbounded priority inversion, let us look at the following example. We have a resource shown as a green box here, and we have a task T 10 which is executing. It is a low priority task, but then after some time into the execution, it needs the resource. This is a non-preemptable shared resource, and since the resource is available, T 10 starts using the resource. But after it has started using the resource, a very high priority task started executing and it needed the resource, but T 10 cannot be preempted. So, T 2, a very high priority task, waits for T 10 to complete executing the non-preemptable resource, so that T 2 can get it, but unfortunately other tasks like T 3, T 5 etc., these are having priority more than T 10, and they become ready and start using the CPU. And since these are higher priority than T 10, T 10 is preempted and it cannot complete its execution, and meanwhile T 2 keeps on waiting. Here a simple priority inversion occurs when T 2 is simply waiting for T 10, but then the unbounded priority inversion occurs where tasks which are of lower priority than T 2, they start executing because they are higher priority than T 10, and T 2 undergoes many priority inversion, one due to T 10 initially, then later due to T 5, T 3, T 7 etc. To explain the concept, we have another schematic example here. On the x axis here we have plotted the tasks that are using CPU and for how long they are using the CPU. On the y axis we have plotted the tasks. T 1 is the highest priority and T 6 is the lowest priority, and T 2, T 3, T 4, T 5 etc., these are intermediate priority tasks. To start with, T 6 started executing over time and after some time in the execution, it needed a non-preemptable resource, we will call it as a critical resource CR. And since the critical resource was not being used by any other task, it could lock the resource and started using the resource. But then after some time, T 1 became ready. It started executing, preempted T 6 because T 1 is of higher priority, started using the CPU, started executing, but after some time into the execution, it needed the critical resource CR, but then it will not get CR until it is released by T 6. So, the task T 1 waits, but in the meanwhile T 2, T 3, T 4 etc., these are tasks which do not need the resource, they become ready. So, first T 5 became ready, and then as soon as the T 1 blocks for the critical resource, T5 starts executing, but after some time T4 T3 becomes ready and it starts executing, and after some time T4 becomes ready, it starts executing, and T2 becomes ready, starts executing, and again the next instance of T5 becomes ready, starts executing, and so on. And all the while T6 is kept waiting, it cannot really complete its uses of the critical resource. But after a long time, after many priority inversion, each of these tasks is causing a priority inversion to the task T1, and after many priority inversions, task T6 gets the resource, starts executing, and after some time releases the resource, that is unlocks here, and only at that point the T1 task can start executing. So, the task T1 has undergone multiple priority inversion, and in the worst case T6 may never get CPU and T1 may get unbounded priority inversion, where we do not know how many inversions it will undergo. This is another example to explain what is really unbounded priority inversion, because this is an important problem in real time applications. Many applications in the past have failed because they could not take care of the unbounded priority inversion problem adequately. So, here a low priority task TL is holding a non-preemptable resource R. So, TL is in its critical section executing and using the non-preemptable resource R. After some time in the execution, so the x axis is the time axis, a high priority task became ready, and after some time into its execution it needed the resource R, but TL is already locked it, and the high priority task would have to only wait until TL can release the resource. But in the meanwhile, tasks which are higher priority than TL, but lower priority than TH, they keep on arising and executing, and therefore, TL is not able to get the CPU and it cannot complete its execution using the non-preemptable resource, and as a result the high priority task suffers multiple inversions, and we cannot really predict how many inversions it will suffer. If it suffers too many inversions, then it can definitely miss its deadline. In the worst case, the number of priority inversions suffered by a higher priority task can become unbounded, and this situation can cause a high priority task to miss its deadline, and therefore, every real time application developer must take adequate precaution against unbounded priority inversion, must understand what this problem is, when does it arise, and how to overcome the problem of unbounded priority inversion. If the problem is not taken care, then in the worst case, when the worst case situation arises, definitely the high priority task will miss its deadline. Let me repeat again that unless a designer and application real time application developer handles the unbounded priority inversion problem properly, then there will be too many priority inversions and a critical task can miss its deadline. In the past, there have been many examples where the designers could not adequately take care of this and resulted in system failure. Out of these many examples, possibly the most celebrated example is the Mars Pathfinder. Let us see what happened in the Mars Pathfinder. But before we look at what happened in the Mars Pathfinder, let us just understand some simple concepts associated with a critical section, semaphores and priority inversion. Let us assume that two tasks T1 and T3 are sharing resource, a non-preemptable resource which they need to execute in the exclusive mode, and this is the summary of the code of the processes, the tasks T1 and T3, where they do some local processing and then they wait for the semaphore, and once they get access to the semaphore, they access the shared resource and then finally they release the semaphore. The two primitives that are supplied by the operating system for accessing the resource are semaphore wait in typical operating system book. It is denoted by the operation Px, and Vx is the semaphore signal to release the resource, and this part of the code is called as the critical section of the code, and then later they may do more local processing. We are just going to complete this lecture at this point of time, do not have much time left. We will stop here, and from this point we will continue the next lecture. Thank you.